So this will be the review for test 4. And I'm just going to go through some of the questions on the practice test. The first one being, find the sum, I goes from 1 to 50, of 3i squared minus I. So, first of all, let's just write what this is. This is 3 times 1 squared minus 1, right, plus 3 times 2 squared minus 2, plus 3 times 3 squared minus 3, and so on, up until 3 times 50 squared minus 50. So we're not going to obviously add up, 50 numbers here. We're going to use the properties, the rules. So, of course, you can split up the sum of the difference as the difference of the sums. And so at least I hope that's obvious, that you can do this. If not, you should try to convince yourself that you can do this. And of course, the 3 can also come outside the sum. If you multiply 3 times the sum, that's just the sum of 3 times the numbers, right? So this is 3 times the sum I goes from 1 to 50 of I squared minus the sum I goes from 1 to 50 of I. And so now there's nothing else to do but just use, right, the sum of these. And just to remind you, the sum I goes from 1 to n of I is just n times n plus 1 over 2. And the sum I goes from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. Again, you don't have to memorize those. You just look them up. They're in the book. Right, so this will be 3 times, so here n is 50, right? So this will be 50 times 51, and then 2 times 50 is 100, plus 1 is 101, divided by 6. So that's the I squared. And then we have to subtract the sum of the i's, which is the first one here. So this one goes here. So that's where I got the first term from. And then this will just be 50 times 51 over 2. And you just plug all that in your calculator. And you should get 127,500. Okay? Yeah, so way easier than adding up all these numbers here. That would take a lot longer than using the formulas. Okay, so that's question 1. Question 2 is a bit of a challenge, right? Because what we're looking for here, at least in hindsight, right, we're looking for the area under the curve of y equals x squared minus 1 between 1 and 3. So just a very quick graph of this. And I'm going to stretch this out a little bit, right? So we're going from 1 to 3. 3 squares, so we're going up to 8, I believe. So roughly speaking, we want this area in here. Right? And you should know that the easy way to do this, of course, is just to calculate the definite integral from 1 to 3 of x squared minus 1. So why don't we just go ahead and use the shortcut, right? By the fundamental theorem of calculus, we find an antiderivative of x squared minus 1, and that's going to be 1/3 x cubed minus x. And then we evaluate it at 1 and 3, and then just subtract, right? So this will end up being 1/3 of 3 cubed, so 27 over 3 is 9, minus 3. And then you subtract, when you plug in 1, you get 1/3 minus 1. So that's going to be 6 minus negative 2/3, which is 6 2/3, or 20 over 3. So either way. Right, so that should be the exact area of this. And make sure that the point's labeled as 3, 8, right? Okay, so that's not the question, though. The question says to do it by using the definition, which, of course, is the following, right? It's going to be the limit as the sum of the partitions, the norm of the partitions, right, goes to 0 of the sum, I goes from 1 to n, of f of ci, sorry, it should be an I, c sub I, times delta xi. And that's the definition. Actually, that's in 4.3. And this is if you need the delta xi's to be different. In this case, they can all be the same. So this is really just going to be the limit as n goes to infinity of the sum I goes from 1 to n of f of ci. And we'll take that just to be xi, of course, times delta x. So, right, so the interval, of course, is from 1 to 3. And if we want to divide this into n segments, then, right, your delta x is just going to be 3 minus 1 over n, or 2 over n. Right, so all these delta x's here are going to be evenly spaced. Right, so they're all uniform. And the ci's, well, again, you can use the left-hand endpoints or the right-hand endpoints, depending on whether you want an underestimate or an overestimate. I think if we use the left-hand endpoints, we get an overestimate. But once we take the limit, it doesn't matter. So let's see. So for the c, right, so c1 will just be 1. c2 will be 1 plus delta x. Right, so c3 will be 1 plus 2 delta x, and so on, until we get to cn, which will be 1 plus n delta x, which of course will be 3, because that's what b is. And so in the middle here, our ci will just be 1 plus, so it looks like I plus 1 delta x. Right, and so in the end, we'll take the limit of the sum, I goes from 1 to n. And so instead of x, we'll plug in 1 plus I plus 1 delta x. So I think I'm using the right-hand endpoints. So this would end up being an underestimate, but that's okay, right? After the limit, it's not going to matter. Oh, times delta x, I'm sorry. Yeah, so the delta x should go on the outside here. Right, so we know how tedious this is, right? This is not a pleasant calculation, but this is just x squared minus 1. So we're just going to square this mess here, and then minus 1, yes, minus 1, and then all of that times delta x. Of course, delta x is what? It's 2 over n. So, yeah, delta x is just equal to 2 over n. All right. So when you square all this, well, you get 1 squared plus 2 times I plus 1, so 2i plus 2. And then I plus 1 squared is I squared plus 2i plus 1 minus 1. And then all of that times 2 over n. So when we simplify all that, what do we get? We get 1 plus 1 is 2, 2 minus 1 is 1, and then 2i plus 2i is 4i. I just, no, I'm not so sure. So let's see, I squared this, so you get one, yeah, okay, I guess that's right. Because then when you square the I plus 1, you also get I, okay. So I think it's right, and then I squared times 2 over n. Now the 2 over n can come outside the sum, but not the limit, right? The 2 can come outside the limit, of course, it's a constant. But when we take the limit of as n goes to infinity, you can't have the n on the outside of the limit, right? So we'll just say this is 1 over n times, and let me just switch the order here, I squared plus 4i plus 1. Okay. Yeah, so this is just 2 over 1 here. I don't need that. All right. So now we just use the same rules that we did for the first problem, the sum of the i's and the sum of the I squares. So, yep, I'll leave this as 1 over n. So the sum of the I squares, of course, is n times n plus 1 times 2n plus 1 all over 6, plus 4 times I, and that's going to be n times n plus 1 over 2, plus 1. Wait a minute. The sum of the 1's, you're doing n times that, right? So that's just going to be n. Sorry, right? So yeah, this is 1 plus 1 plus 1, right? Sorry. But there's n of them, right? n times 1 is n. Right, so that's where I got this n from. It's not just a 1 anymore. And before we take the limit, of course, we might want to simplify all this. So let's see. I think we can cancel the n's everywhere here. So we're going to end up with 2n squared plus 3n plus 1 all over 6. And then the 4 cancels with the 2. So that'll be a 2 there. So that's just 2n squared plus n. And I forgot to divide by n, so it's just 2n plus 1. Let's see, this is n squared plus n. Yeah, when you divide by n, you just get 2n plus 2, because you got to distribute the 2. And then n divided by n is 1. So now that's a 1 again. So yep, I canceled all the n's here. And I know I'm doing this fast, but again, this is very poor canceling there. But I see students do it all the time, and I'd love to say, please don't do that, because you should distribute the 1 over n first. But again, I want to go through this quickly here. So now, I think all that's left is a big problem, because this is just going to go to infinity. So I think I'm missing something in the denominators here. So let me go back and check. What am I missing? So f of ci, this looks right. This is the f of ci, and ci was this. Oh, I forgot the delta x. Oh, you know, I had it there and I erased it. Oh, I had it right the first time. I thought that was this delta x, but there's another delta x here. All right, so that's where I went wrong. So hang on a second, I'm going to fix that. Okay, yep, so there should be a delta x after the I plus 1. That's this thing here. Yep, so that's my CI. And yeah, so delta x is again 2 over n. So, right, so now how is that going to affect this? Well, the 1 in front stays the same. That does not get multiplied by the 2 over n, but everything else does here. So, so that means, let's see. All right, well, let's just start over. Let's do this again. Okay, so yeah, very easy to make that little mistake there. All right, so this is still in the brackets here. 1 squared is 1, and then we get 2 times this, so you're going to get 4 over n times the I plus 1, and then you're going to get 4 over n squared times I squared plus 2I plus 1, and then minus 1, and then another factor of 2 over n. Yeah, so that changes everything, right? All right, so in this case, we can just subtract 1 minus 1 is 0. And then we're going to get, let's see, 4 over n. So that can come outside the sum here. Although, yeah, okay, so 4 over n, and then times I plus 1, and then plus 4 over n squared, times the sum, I goes from 1 to n, of I squared plus 2I plus 1. And all of this is multiplied by 2 over n. So I could have left the 2 on the outside here, but this is all over n. So we're going to get n squared here, and then n cubed here. Okay. So I think that's it. Let's hope that's right. All right, so we still have 4 over n squared, and then I is n times n plus 1 over 2 plus n, and then plus the 4 over n cubed, and then I squared is n times n plus 1 times 2n plus 1, over 6, plus 2 times I, so 2n, n plus 1 over 2, and cancel the 2's, plus 1, so the n of those will be n again. Okay. So I think this is better now. So what are we going to get here? 4 over 2 is 2, and then you get n squared plus n all over n squared. And then you get 4n over n squared. And then, well, let's do the second series here separately. 4 over 6 is 2 over 3. And then, oh boy, so all of this becomes 2n cubed plus 3n squared plus n. When you divide, well, all right, we'll divide that by n cubed in just a second. N cubed, yep. And then what do we get here? So 4n squared plus 4n over n cubed plus 4n over n cubed. Okay. It's a mess, but I think we can handle this now. So here the n squares cancel, so you just get 2 plus 2 over n plus 4 over n. And then, yeah, let's just continue. So this is 2/3 times 2, so that's 4/3 times 1. And then everything else will just have an n in the denominator. So I think this is 2 over n plus 2 over 3n squared. And then here, we're just going to get 4 over n plus 4 over n squared plus another 4 over n squared. So let's just make that 8 over n squared. And this is all times 2 in front, right? So now taking the limit should be pretty easy. What do we get? We get 2 plus 0 plus 0 plus 4/3 plus 0 plus 0 plus 0 plus 0. So 2 plus 4/3 is 10/3. And then when you multiply by 2, you get 20 over 3. And that was the same answer we got. Obviously, a lot easier using the shortcut here. We got 20 over 3. And again, if I didn't have this delta x in here, then I would have gotten infinity, which of course is nonsense. The area is not infinite. But there you go. That's number 2. And honestly, I really wouldn't worry about that. This is obviously not a very good test question. Though, I mean, before you take the limit, if you simplify all this mess here, it gives you the underestimate. So this will just, you can plug in n is equal to, n is the number of rectangles, right? The number of intervals that you're dividing this up, right? So if you want 10 rectangles, n is 10. If you want 1,000 rectangles, n is 1,000. But when the number of rectangles gets bigger and bigger, the total area approaches about 6 2/3. So 20 over 3. But like I say, not a very good test question. I could, of course, ask, find the area for 4 rectangles or 6 rectangles, but not the exact area. If I wanted the exact area, yeah, you should calculate this definite integral because that's so much easier, right? All right, so on to number 3. Yeah, this should be a quick one, right? Because remember, f is even. Remember what that means? It means f of negative x equals f of x, right? And g is odd. So that means g of minus x is minus g of x. So to calculate these integrals here, so from -4 to +4, well, what are we given? We're given the integral from 0 to 4. But if f is even, well, then we have the property that this is just 2 times the definite integral from 0 to 4 of f of x. And since that, right, this number is given, this is 5, then the answer has to be 10. Right? And I'm pretty sure in section 4.3, I believe, I explained why this property is true. It just has to do with when you have an even function, right? You're just doubling the, no, that doesn't look right. It should be symmetric, right? From -a to +a, you're just doubling the area from 0 to a, right? Okay, so there it is again. For part B, the integral from -4 to 4 of g of x, well, remember, g is odd, so if you're going from -a to +a, you just get 0, right? And that's because g is odd. Nothing more to say there, right? For part C, we want the definite integral from 0 to 4 of f of x plus g of x. So that's the sum of two functions. And you should know by now that the sum rule applies. So you can split this up as the sum of the integral, well, yeah, the sum of the two integrals, right, from 0 to 4. Right. And these were given above, right? These were 5 and 9. So 5 plus 9, 14. So that's just by the sum rule. Oh, I can just squeeze this in here, right? So we're going from -4 to 4 of f of x times g of x. Now here you have to be careful because there's no product rule, right? You cannot say that this is the definite integral from -4 to 4 of f of x times the definite integral from -4 to 4 of g of x. If you do that, it's wrong. However, you happen to get the right answer here, but for the wrong reason. Okay, so you do get 0, right? The answer is 0, but the reason is because f of x times g of x, it's the same reason as in part B. This is an odd function, right? The product of an even function and an odd function is an odd function. Right? And you should know how to prove that. Right? Or at least be able to demonstrate it. Right? I mean, just think of a typical even function. Right? X squared is an even function, right? Think of an odd function, x cubed. So what happens when you multiply f times g? You get x squared times x cubed, which is x to the fifth. Well, 5 is odd, so this is an odd function, right? So that doesn't prove it, but that's a pretty good reason why you would expect that this would be an odd function. So it's really the same reason as in part B. However, if you do it this way, you'll get credit for the right answer, but it's the wrong reason, right? There is no product rule. There's no product rule for integrals, only for derivatives, right? There is a sum rule, which we used in part C, but no product rule, right? So by coincidence, you happen to get the right answer, right? You get, whatever it is, 5 times 0, but that does not work in general. It's just a coincidence. Number 4 seems like a hard one, but it really isn't, right? We want to find the upper and lower limits of the integral, right? So the integral being the definite integral from a to b of 3x minus x squared dx, right? And we want to maximize, I can spell, maximize the value of this definite integral. Why does this keep moving here? All right. Okay. So, yep. So how do we maximize this? And keep in mind, it depends on both a and b. So if you're thinking, take the derivative, set it equal to 0, again, it's a function of both a and b. And we don't know how to take derivatives of those. Well, maybe some of you do. They're partial derivatives, but again, that's way beyond what we want to do here. Instead, they give us a hint, right? The hint is to graph the integrand. So, I think we can handle that. This is 3x minus x squared. So 1, 2, 3, 4. So yeah, this is just a parabola. Keeps going this way. So a little sloppy, but good enough. So what are we trying to do? If we're trying to maximize this definite integral, what does this definite integral represent? Well, it represents the area between a and b. So let's say my a is 1, and my b is, 2.5. Then I want the area of this region, right? So that's a pretty big area. Can I make it bigger? Well, sure. If I go from, say, 1/2 to 2.5, now I'm including this area. Right? Can I make it bigger? Sure. Start at 0. Then I include this tiny little piece in here. Right? And why stop at 2.5? Why not go all the way to 3? So that's a pretty big area. I can't fill in the whole thing, but let's just suppose that that's the area, right? And you might ask, well, maybe I can make that area bigger. Suppose I go all the way to 4. And this is way down here somewhere. Well, let's see. 3 times 4 is 12. 12 minus 4 squared. 12 minus 16 is -4. Okay, so it's not to scale, obviously, because this is only 4, -4 down here. Right. So, sure, if I go all the way to 4, right, if I go from 0 to 4, I'm including this area as well. However, this area is below the x-axis, right? So that would actually subtract from this area, the red area, right? So no, by going to 4, you're actually making the integral smaller. You're not adding the purple area, you're subtracting the red area minus the purple area. So you're getting a smaller number, right? And the same is true if you want x to be, say, -1/2. This area would end up getting subtracted. So the maximum area you can get that's above the x-axis is this red area here, and to get that full area, you're going from 0 to 3. So a should be 0, b should be 3, and that will give you the maximum area. And that's all you can say about that. Okay, on to number 5, and I don't think I'm going to do all of these, but I'll do a few. A should be really easy. 4 minus 3x to the 5th power dx, right? So the substitution here, of course, is just u is equal to 4 minus 3x, which means du is just negative 3, right, times dx. So we're missing a negative 3, so we'll multiply by negative 1/3 on the outside. Okay, I'll write it out, right, times negative 3 on the inside, right? So this will end up just being u to the 5th power. This is just du. So we have negative 1/3 times the integral of u to the 5 du. So by the power rule, this is going to be 1 over 6 times u to the 6. Don't forget your c. So I think in the end we just get negative 1 over 18 times u to the 6 plus c. Right. Oh, and maybe replace u with 4 minus 3x. So since I'm running out of space, let's do it here. So the answer should be negative 1 over 18 times 4 minus 3x to the 6th power plus c. Okay. Part B, square root of tangent times secant squared. I think that's also a fairly routine one. Oh, okay, x or theta, doesn't matter. I'll stick with the question that has theta. So in this case, my u, of course, should be tangent, because the derivative of tangent, as you all know by now, is secant squared. Right? So the secant squared d theta is du, and then this is going to be the square root of u. So we're just doing the integral of the square root of u du, right? And power rule, u to the 1/2. So this will be 2/3 times u to the 3 over 2 plus c. And then, of course, u was tangent. So 2/3 times tangent theta to the power 3 over 2 plus c. All right, going on to part C now. Part C was what? So it was the integral, oops, I don't need b there, right? Okay, so let's try that again. The integral of z minus 1 all over 8z squared minus 16z with respect to z. So let's see, the biggest power is in the denominator, so it's not like we can divide these, right? It's a proper fraction. On the other hand, let's just take the derivative of the denominator. So let's see if u is the denominator. Just a guess, right? So the derivative will be 16 times z minus 16, right? Which is not the numerator. However, if you factor out the 16, there's your z minus 1, right? So apparently we just need a factor of 16 in the numerator. I'm just copying this down again. And yeah, you can think of the dz as being multiplied by the numerator here. So, yep, we're just missing the 16 here to make it du, to make the numerator du, but then you also have to divide by 16. At least that's my favorite way of doing this. So the numerator is du, the denominator is u. So the power rule does not apply here, right? It's u to the negative 1. Right? But hopefully by now, having been through all of chapter 5, you know that this integral is just the natural log of absolute value of u. Don't forget the absolute value. Also, don't forget the c here. And what was u? It was 8z squared is supposed to be an 8. So absolute value of 8z squared minus 16 times z plus z. And yeah, I think we can simplify this further, but I'm willing to bet this is probably the answer in the back. And if not, this is fine. You can leave it like this. All right. Oh boy, I know I said I wasn't going to do them all, but let's do part D. Square root of x times 1 plus x minus the cube root of x with respect to x. Well, there's parentheses, so this is a product. But as I mentioned earlier, there is no product rule, right? Which means we need another way to do this, right? You can think of a substitution here, but I don't think that's going to help, right? Whatever you select to be your u is probably not going to end up working to have a du as another factor. So, oh gosh, this keeps moving. Right. So the idea is just multiply it out, right? This is x to the 1/2 times 1 plus x minus x to the 1/3. Right? So you just get x to the 1/2 plus x to the 3/2 minus x to the 1/2 plus 1/3 is 5/6. So now you just use the sum and difference rule, and you integrate each using the power rule. So you're going to get, again, 2/3 x to the 3/2 plus, and then 3/2 plus 1 is 5/2. So 2/5 x to the 5/2, and then minus, so 5/6 plus 1 is 11/6. So 6/11 times x to the 11/6, and don't forget your c. So, yep, up until, right, so A, B, and C pretty much required a substitution. Although you could do part A by multiplying it out. I wouldn't. That would take way longer than doing it by substitution. But B and C certainly needed the substitution, I think. D did not. D, I think, is one of the few questions where you do not need a substitution here. So I could have asked you this problem way back in 4.1. And I probably did a similar one using powers. Okay, so I guess we'll do E as well. So E is the definite integral of 4 times t over the square root of t squared plus 1 with respect to t. Okay, so notice that the 4 is a constant. We can easily just bring that outside. I mean, you don't have to, but I prefer to do it that way. And then the denominator is just t squared plus 1 to the 1/2. So really, this is 4 times the integral of t squared plus 1 to the negative 1/2 times t times dt. So you see where I'm setting this up for, right? My u should be what's in the parentheses or what's under the square root. So u should be t squared plus 1, which means du is 2t dt. So I have the t dt. What I don't have is the 2. So multiply by 2 and divide by 2. And when you do that, you get 2 times the integral of u to the negative 1/2. And then all of this is just du. And now we can just use the power rule. Negative 1/2 plus 1 is positive 1/2. Right, divided by 1/2, right, and that's just multiplied by 2, so 4u to the 1/2 plus c, and so that's really just 4 times the square root of u plus c, and what was u? It was t squared plus 1. So that should be the answer for part E. Part F. This is not going to be a fun one, I think. So again, whenever you see a square root, your first instinct, just as it would be if you were taking the derivative, is to change it to x plus 3 to the 1/2. So no problem there. But now we have a problem because this is a product, right? You're multiplying these, but there's no product rule. And there's no easy way to multiply this out, right? It's not like you can, you can bring the x squared inside to make it x to the 4th, right? So you can simplify this as x to the 5th plus 3x to the 4th. But honestly, that doesn't make the problem any easier. In fact, I think it makes it harder. So that's not the answer. That's not the way to go here. As far as I know, there's no good way to do that. So I think the only choice is to do some sort of a substitution, and it's either going to be u equals x squared, but I don't think that's going to work because the du is not even close, right? This is not, x to the 1/2, so that doesn't work. Yeah, as strange as this seems, I think u is just x plus 3, right? So it's just the shift by 3 here. So du is just dx, right? The derivative is 1, so 1 times dx. So how is that going to work? Because we have x squared times u to the 1/2 du, but as I mentioned several times, you can't mix your x's and u's. So what can I do? Well, right, I know what x is. It's just u minus 3. So I can plug that in here and change x to u minus 3. And now everything is in terms of u. So now this should work out, right? Now it should be doable, and I'm running out of space, so I'm a little worried that I can squeeze all this in here. All right, well, so I might have to go to the right a little bit here and maybe squeeze it in here. So notice that there's still an issue because this is a product and there's no product rule. But unlike up here where we said we couldn't really do anything with that, here we could multiply this out, right? If you multiply it out, you're going to get u squared times u to the 1/2, so that's u to the 5/2, minus 6 times u to the 3/2, plus 9 u to the 1/2. Right? And now this is looking a lot like, I guess, part D rather. And so I think we can do that. Sum rule and product rule, and sorry, not product rule, constant times function rule, and the power rule. Right? So you're going to get 2/7 u to the 7/2 minus 6 times 2/5, it's a 5, u to the 5/2 plus 9 times 2/3 u to the 3/2. And that's the integral, right? So don't forget your plus c here. Right. So now I'm going to do two things here to simplify this. I can factor out a common factor of u to the 3/2. And I'm wondering if I should take out a common factor here, but we can always do that later. So u to the 3/2 is the lowest power of x. So what is that going to multiply? That's going to multiply 2/7 times u to the 4/2, so that's u squared. And then minus, let's see, 12/5. And that's going to be u to the 1. And then 18/3 is just 6. Okay. And then plus c. Yeah, so I think I could have factored out a 2 here. So maybe let's just do that now. So this is, well, maybe I should also get a common denominator here, which is what, 35? So 2/35. Oh, now I'm filling this up though. So I better end this quick. Yeah, so 2 over 35, so that means this is going to be 5u squared minus 6 times 7, it's 42u, and then 6 times 35, calculator, 6 times 35 is 210, so plus 210, and then plus c. Right, and this is looking pretty good, except remember, u is x plus 3. So 2 over 35 times x plus 3 to the 3 halves times 5 times x plus 3 squared minus 42 times x plus 3 plus 210, all plus c here. And you should probably expand this out as well. So 2 over 3 times x plus 3 to the 3 halves, that'll stay on the outside. This will end up being what? X squared times 5, so 5x squared plus 6 times 5 is 30, so 30x plus 9 times 5 is 45. And then we have minus 42x minus 126 plus 210. So, yeah, you know what? You can simplify that. That's right. 30 minus 42x is negative 12x, and then 45 minus 126 plus 210. All right, so that's pretty close to the answer. Let's see what I had for the answer, if it's anything like that. So I kind of left it in this form up here, just replacing u with the x plus 3. So, all right, feel free to do that, but I kind of prefer to factor out the x plus 3 to the 3 halves. All right, enough of f. That was a tough one. Let's try an easier one. Yeah, so g should be routine at this point. Just recognizing that the derivative of theta is 1 and the derivative of sine is cosine. So u should be what's under the fourth root, theta plus sine of theta. So that du is just the numerator, 1 plus cosine theta d theta, in parentheses, right? So this is just going to be du over the fourth root of u, or if you prefer, u to the negative 1/4 du. And when you integrate that, negative 1/4 plus 1 is 3 over 4. So 4 over 3, u to the 3/4 plus c, and just replace u with theta plus sine theta. So, yeah, so that's, I would consider that to be a very reasonable question. H is a little tricky. So maybe let's do h. Cosine to the 4th times sine cubed. This is more sort of in preparation for Calc 2. You're going to see this a lot in Calc 2. So maybe a little premature to talk about things like this in Calc 1. But here's the idea, right? If you let u be cosine, then the derivative will be negative sine, but not negative sine to the 3rd. Okay, so here's the trick, right? If I have cosine to the 4th, right, and then sine cubed, I can think of that as sine squared times sine. All right? And notice that sine squared is just 1 minus cosine squared, Pythagorean identity. And so now the du is just the negative sine x, right? So at this stage here, and in fact, I'm going to multiply this out. We're going to get cosine to the 4th minus cosine to the 6th. times sine of x dx. Right? And this is where you would substitute. U is going to be cosine. I think I'm doing this in the wrong place. So yeah, u is going to be cosine of x, and the derivative of that is negative sine x dx. So where's the negative? Well, there isn't any, so let's multiply by negative 1 and divide by negative 1, which is the same as multiplying by negative 1, right? So you get a negative integral of u to the 4th minus u to the 6th, and then all of this is du. So keep the negative, use the power rule. And then don't forget your plus c. So I think we can distribute the negative, and what we're going to get is 1 over 7 times u, which is cosine of x to the 7th, minus 1 over 5 times cosine of x to the 5th, plus c. You can leave it like that, or as is convention, you can write cosine to the 7th over 7 minus cosine to the 5th over 5 plus c. Doesn't matter to me. Yeah, so this involved a rather clever trick here of splitting up the sine cubed of x as sine squared times sine to the 1. Are there other ways of doing it? Yeah, possibly, but this is what comes to mind when I do it, right? And so you kind of got to get used to these little techniques here. So if you didn't get that, don't worry about it. But when you take Calc 2, hopefully you'll remember these type of techniques because it's fairly common in Calculus 2. Okay, part I. We're doing this integral here, x cubed plus 3x squared minus 4x minus 4 over x plus 3. And, we've had this rule of thumb where u should just be the denominator, x plus 3. Right? And that's one way to do this. It's not the way I would prefer to do it at this point because it does make the numerator, well, right, you would replace x with u minus 3, and that's going to take a while to multiply out. So if you want to do it that way, go right ahead. There's no problem with that. It's just a lot of work, and it's kind of tedious. The way I prefer to do this is notice that the bigger power is in the numerator. So that means we can do the division, right? We can divide x cubed plus 3x squared minus 4x minus 4 divided by x plus 3. And of course, I'm not going to do using long division. I'm going to do synthetic division, which I hope you're all comfortable with. So that's a 0, negative 4, positive 12, and 8. So these are the coefficients. When you divide, you're just going to get x squared plus 0x minus 4, and then plus 8 divided by x plus 3. Okay. So notice that's the integrand, right? We didn't integrate anything yet. All we're doing is rewriting this fraction here as x squared minus 4 plus 8 over x plus 3. Okay. Now, I think this should be pretty easy because you're just integrating x squared, you're integrating 4 or negative 4, and so the only non-trivial one is this. I'll take the 8 outside. It's dx over x plus 3. So let's do the first term. This is 1/3 x cubed, right, minus 4x plus 8 times what? Right, and then plus c, of course. So here we need a little mini substitution. U is the denominator, right? Again, we were going to do that right away. That would have been fine. But now we got to do it here for sure. So here we're just going to get the integral of du over u, which is natural log of absolute value of u. And so you're just going to get natural log of x plus 3 in absolute value, of course. So personally, I think this was the easiest way to do it. And if you did it the other way, you should get the same answer, although you may not, right? You may get another number in here, and I forget what number it is, but let's say you add you add this, plus 15 or something. So where's the 15 here? I don't see it. It's there, right? C is a number, 15 is a number. So if you do it the other way and you get, say, a plus 15 somewhere, you could just absorb that into the C. It's a number, right? So you don't have to. You can leave it as plus 15 or whatever number that is. But the point is, you don't need it there because it's a constant. And so the C takes care of any such number, right? Right. In other words, it doesn't matter what number I add to this, it's still going to be correct, right? If I say that the answer is this plus 120 million, right, it's the same answer. It's just that, this C here is 120 million less than this C. So, right, or actually 120 million more. But it doesn't matter, right? So adding the 120 million doesn't do anything because it's just a constant. All right, I'm going to do maybe one more. I really want to move on to some of the trickier problems as well. Okay, so here's J, and I don't think this is going to be that difficult. You don't want u to be x, right? If you just do u equals x, you're generally not going to change anything. You're just going to make them all u's instead of x's, right? X. So how about u is just the entire denominator, right? The square root of x plus 1. Right? And in fact, we could solve for x here, right? The square root of x is just u minus 1. So the numerator is u minus 1, the denominator is u, and what's dx? So I'm going to square both sides. You don't have to, but I think it might make it easier to take the derivative using the power rule. And the derivative of u minus 1 is just 1, so it's just 2 times u minus 1 du. So 2 times u minus 1 du. So the 2 can come in front, that's just a constant. And then we have u minus 1 times u minus 1, so u minus 1 squared over u. Well, let's multiply that out. And again, just do the division, right? You get u minus 2 plus 1 over u. So you multiply all this by u here, you just get 1/2 u squared minus 2u plus natural log of absolute value of u plus c. Or, well, the 2 times 1/2 is 1, so I guess we're going to get u squared minus 4u plus 2 natural log of absolute value of u plus c. And what was u? U was the square root of x plus 1. So square root of x plus 1 squared minus 4 times square root of x plus 1 plus 2 times the natural log of, in this case, we don't need absolute value because square root of x plus 1 is positive. And again, we could leave it like that, but maybe we should multiply this out. 2 here. That's a 4 square root of x minus 4. Yep, we're not going to be able to simplify this. Natural log of square root of x plus 1. So we're just going to get x, and then 2 square root of x minus 4 square root of x is negative 2 square root of x. 1 minus 4 is negative 3, plus 2 times natural log of, again, if you want to put absolute value, that's fine. But in this case, it's not necessary because it's already positive. Oh, and that's it, right? Good enough. And as I mentioned earlier, in the previous one, I think, x minus 2 square root of x plus 2 natural log of, again, absolute value, doesn't matter, square root of x plus 1, and then plus c. Same thing, right? Same answer. So if you're asking the question, where did I put the negative 3 here? Well, I just answered that just maybe 5 minutes ago, right? It got absorbed into the c, right? So yes, this c is not the same as this c, right? This c here is 3 less than this c, c minus 3, but that's okay. It's just a different c. Well, I guess I'll finish the last two. So the integral of x to the negative 2 times e to the 1 over x dx. So again, it's a product. There's no product rule. On the other hand, maybe if I write it like this might help. Right? So the exponent of e is x to the negative 1. And what's the derivative of x to the negative 1? Well, negative x to the negative 2. And there's your x to the negative 2, right? So in other words, this was just written backwards. Oh, sorry, it's not negative x to the negative 1. It's just e to the x to the negative 1, and then times x to the negative 2 dx. So of course we're missing a minus sign here. We can just bring that outside. And this is just negative the integral of e to the u du, which of course is just e to the u, or negative e to the u, right, plus c. And of course u was 1 over x, so you just get negative e to the 1 over x plus c. All right, and finally part L. Very quickly here, part L is the integral of x plus log x times x plus 1 over x. Right. And there's a very good reason for writing it this particular way. Of course, I could have started multiplying stuff out, and that would actually make it harder. So the thing to note here, so I can't do much with x plus log x, but I could rewrite the second factor as 1 plus 1 over x. And that should look pretty easy now. If u is just x plus log x, the derivative of that is 1 plus 1 over x. Right? So, yep, this is my du, this is u, so you get the integral of u du, which is 1/2 u squared plus c, and u was x plus log x. Okay, so those are the indefinite integrals. So number 6, very good application problem. This is something you might see in a physics course, right, or a dynamics course maybe. But yeah, right, so you're launching a ball upward from the ground level, so we'll say that this is height 0. Instead of using s, how about if I just use y for the height? So this is y equals 0. So what happens? The ball goes up and it comes down. No surprise, right? And so once you launch it, the only thing affecting it is gravity, and gravity has an acceleration of, well, I guess we should call it negative, right? Negative 32 feet per second squared. Right? And so if that's the acceleration, to get the velocity, you have to integrate it, right? And since it's just a number, the integral is just negative 32 times t plus c. So what's c going to be? Well, if we think of this as a function of t now, t plus c, and I plug in t equals 0, negative 32 times 0 is 0, I just get c. In other words, c is just the velocity at time t equals 0, and rather than write v parentheses 0, we typically write v subscript 0 to represent the initial velocity. Right. So you can say v0 or v0, as is usually the case. So, yep, the velocity as a function of t is just negative 32t plus v0. And in this case, they tell us the initial velocity. The initial velocity is 96 feet per second. So I didn't need the v0 here. We'll change that to 96 feet per second, right? Yeah, doesn't look right. Yep. So now we have the velocity as a function of time. But notice that in part D, they ask us about the height. So the height is y, the position. So to get the position, we have to integrate the velocity. And this is also a rather trivial integral. It's just negative 16t squared plus 96t plus another c. So it's a different c here. And if you plug in t equals 0, you just get c. So that's going to be y0, or the initial height, right? So y of t will be negative 16t squared plus 96t plus, sorry, not g0, but y0. And the initial height is also given. It may not, right, you have to read it carefully, right? It's launched upward from the ground. The ground is what we're calling y equals 0, right? So that means y0 is, well, 0 feet, right? So for that, we don't need the y0 here. We're just adding 0, right? It's my terrible eraser, but okay. So now we have both the velocity and the height as a function of time. And the rest is either really just plugging in numbers or solving equations. So I think you can handle that, or at least I hope at this point it's easy. So question A, how long does it take for the ball to reach the maximum height? Well, at the maximum height here, right, it's going up, it's coming down, the velocity is 0. So part A is just asking for, when is the velocity equal to 0? So you just solve this equation, and you get t is equal to, well, 96 over 32, which is 3 seconds. Let's try that again, 3 seconds. Okay. Part B, what is the maximum height? Sorry, this is not my intention. Having technical problems. All right, so part B, what is the maximum height? Well, the height occurs at 3 seconds. So just plug in 3 into the height function. Negative 16 times 3 squared plus 96 times 3. And it's 144. So 144 feet. So that's as high as it goes. So this is 144 feet here, right? How long does it take for the ball to reach half the initial velocity? Again, easy question. Half the initial velocity is half of 96, which is 48. So when is the velocity, this is part C now, when is the velocity equal to 48? Now you solve this equation, and I think you get t is, well, 1.5 seconds, 1.5 seconds. So now you have to be careful here, because you might just assume, well, if the question was how long does it take to reach a third of the initial velocity, you might think that it's a third of 3 seconds. It might be 1 second. I don't think it works that way, so be very careful about that. That's just a coincidence. And in fact, in part D, what was the question? What is the height of the ball when the velocity is, so when t is 1.5 seconds, what is the height? So now you're just plugging in 1.5 again into the height function. Right. But you don't get half the height, right? In other words, you don't get 72 feet here. I think you get 108, if I remember right. 108 feet. So there you go. Once you integrate to get the velocity and the height function, y is the height function. I'll mention that's height. And it's either solving equations or plugging in numbers, which, you know, is a big part of physics, right? It's right. If you know the formulas, or if you have the formulas, plugging in numbers is not the hard part, at least in my opinion. And number 7, so wow, we just finished doing all those indefinite integrals. Now we're doing definite integrals. And, well, all right. I know I keep saying I'm not going to do all of them, but I might. No, I'm going to skip a few here. So let's start with A, which is fairly routine. We're going from -1 to -3 of v minus 1 over v squared dv. Right? So we just integrate, and we get 1/2 v squared plus 1 over v. Right? No c here because we're just going to plug in the -1 and the -3. So when you plug in -3, you get 9 over 2, and that's going to be minus 1/3. And when you plug in the -1, you just get 1/2 minus 1, and that's, oh boy, I want to say 25 over 6, and then minus -1/2, so plus 1/2. So 28 over 6, which is 14 over 3. So part A, I don't know why I'm putting it here. Part A is just 14 over 3. Okay, so part B, t squared plus 1 times the square root of t, or t to the 1/2. And we're integrating from 4 to 9, right? So this is going to be t to the 5 over 2 plus t to the 1 over 2. Right? Again, there's no product rule, so I just multiply this out here. Right, and so you're going to get 2 over 7 t to the 7 over 2 plus 2 over 3 t to the 3 over 2 as the indefinite integral. Now you just plug in the 9 and the 4. So when you plug in 9, you get 3 to the 7 divided by, yeah, so 2/7, 3 to the 7, plus 2/3 times, let's see, 3 to the 3, which is 27. And then minus, square root of 4 is 2, so 2/7, 2 to the 7, plus minus 2/3, as you're subtracting them both, of 2 to the 3, which is 8. So whatever that is, you know what? That's just arithmetic. Go ahead and do that. I'm thinking the answer is 12,620 over 21, but that's what's in the answer key, so I'm hoping that's right. And then what are we up to? Part C. Yeah, so that's not an obvious one. Part C, we have the definite integral from 0 to 4 of the absolute value of x squared minus 4 dx. So, right, so what's difficult about this is that we're integrating the absolute value, and I don't think we ever did this. We don't know the indefinite integral. So how are we supposed to find the definite integral? So yeah, good question, right? Well, maybe we don't even need to find the indefinite integral, right? Remember, what does the definite integral represent? It represents the area underneath the curve. So if we just graph this, x squared minus 4 4, here's 4, here's 2. Well, x squared minus 4 is just the parabola right, 2 squared, right, so it's 0 at 2. Yeah, so it's just x squared shifted down 4 units. So down here somewhere. Yeah. So something like this. I know I'm being a little careless here. But so what happens when you take the absolute value? This gets flipped upside down here, right? So that means this. Oops, I'm trying to erase it. So I think that's right. X squared minus 4. So if x is 0, yep, this is going to be 4 up here. So y is 4. And 4 squared is 16. 16 minus 4 is 12. So I could do a better job than that. It's going to look... Right, so this is going to be 412. Right, and I had it right. Yeah, I had it right the first time. So just flip it upside down, and it'll look something like that, I think. Yep. All right, good enough. So find the area from 0 to 2, and then from 2 to 4. So that's the idea. Split it up into 2 parts here. So here, this is going to be the opposite, 4 minus x squared. And then when you go from 2 to 4, you just get x squared minus 4. Okay. So at this point, I think you can handle all that. You should get 16. Right. Yeah, so when you see absolute value, you might have to graph it. You might have to split it up where it splits, right? Where the integrand is equal to 0, right? Where the absolute value is equal to 0, and that's going to be at -2 and +2. But if we're only going from 0 to 4, we don't bother with the -2. It's just going to be symmetric here. It's going to look like that. It's going to be just this big W, right? So that's part C. Kind of a tricky one because if you're trying to do it by finding the indefinite integral, that's going to be a little bit tricky. On the other hand, this is one that you will be able to do this in Calc 2. So this is a Calc 2 problem to find the indefinite integral of the absolute value of x. And it's actually not a very hard problem in Calc 2. It just involves integration by parts. Right, so going on to part D. This is the definite integral from 0 to pi over 8 of secant squared theta divided by tangent squared theta plus 1. Again, seems like a very hard problem unless you have the Pythagorean identity. 1 plus tangent squared is the same as secant squared, which of course is the same as tangent squared plus 1. So the denominator is just secant squared. And secant squared divided by secant squared is 1. Okay. So if you're trying to do substitution or anything like that, you're really making it a lot harder than it has to be. Right? This is just pi over 8 minus 0, which of course is pi over 8. So, yep, so don't make it harder than it has to be. Right? This was a really easy problem. If you recognize that this is just equal to 1, then that's a very easy integral to do. It's just theta, right? Okay, part E. Now we're getting a little bit harder. We have x cubed over the square root of x to the 4th plus 9 dx from 0 to 1. So here, I don't think we're going to be able to simplify this at all. I think our only hope is to do a substitution. U is x to the fourth plus 9. So that du is 4x cubed dx. So we have the x cubed. We don't have the 4, so multiply and divide by it. And then you're just going to get u to the negative 1/2 du. Now notice, I'm not putting 0 and 1 here because that would be wrong. If x is 0, then u is going to be, well, I should write that out. Sorry. If x is 0, right, u is going to be 0 plus 9, which is 9. If x is 1, then u is going to be 1 plus 9, which is 10. So we're actually integrating from 9 to 10 now. And the integral of u to the negative 1/2 is just 2 times the square root of u. From 9 to 10. And 2 over 4 is just 1/2. So this is really just the square root of u over 2 evaluated between 9 and 10. So you get the square root of 10 over 2 minus the square root of 9 over 2, which is the square root of 10 minus 3 all over 2. So I guess that's it for part E. And for part F, well, so the 6 can come outside. That's just a constant. Tangent of 3x, right? So this is going to require a miniature substitution. U is 3x, du is 3 dx. So we need to multiply by 3 and divide by 3. And in that case, we get 2 times the integral of tangent of u du. And we're integrating from 0, and then 3 times pi over 12 is just pi over 4. Okay, so what's the integral of tangent of u? So, right, sine over cosine, so I think it's just going to be natural log of absolute value of cosine of u. Right? Wait, is there a negative? Let's see, sine over cosine, the derivative of cosine is negative sign. Yep, so there should be a minus sign here. Sometimes forget the minus sign. Yep, so negative 2 log of cosine of u to the pi over 4. Of course, you can, if you want to dispense with the negative sign, you can just flip this around and do it the other way, subtract in the other direction. Yeah, so we're just going to get the natural, 2 times the natural log of cosine of 0 minus 2 times the natural log of cosine of pi over 4. And here we don't really need the absolute value, of course, because these are positive. 2 times the natural log of 1 minus 2 times the natural log of square root of 2 over 2. Natural log of 1 is 0. And then this is the natural log of the square root of 2, minus the natural log of 2. And natural log of, well, okay, so negative 2, natural log of 2 to the 1/2, we can bring the 1/2 in front, plus 2 log 2. So this is just going to be negative log 2 plus 2 log 2, which is log 2. Hang on. So I looked this over again, and I don't see anything I did wrong here. So the answer, the answer should just be natural log of 2. And so the answer key, I think, is wrong. The answer key has 2 square root of 2 minus 2, which is definitely not the same thing. Wow. So I'm still amazed. I'm still finding mistakes in the answer key. So the answer key is wrong. Answer key wrong for F. What is this? 7F. Yeah. Okay, well, I'm glad I did it then. Like I say, the answer key is 99% correct, but occasionally there will still be these little mistakes. So natural log 2 should be the answer. 2 squared root of 2 minus 2, I don't know where that came from. Sorry about that. But going on to part G. Yeah, this should be a very easy one. All you have to do is simplify, right? This is 2x plus 1 over x. So when you integrate, you just get x squared plus natural log of absolute value of x. However, we don't need absolute value because both 1 and 4 are positive. So you get 4 squared plus natural log of 4 minus 1 squared minus natural log of 1. Natural log of 1 is 0. So 16 minus 1 is 15 plus the natural log of 4. Or if you prefer, 15 plus 2 log 2. I think I wrote this in the answer key, which is fine. This is equivalent. You should know that. And then h is also very quick and easy. At least I hope so. The integral from 1 to e squared. That's a weird number, but you'll see it works out pretty nice. Of log x over x. Okay. So there's no quotient rule. And even if there was, we don't know the integral of log x. Well, at least, sorry, I'm moving it up a little. At least you probably don't. Some of you might. But again, there's no quotient rule, right? So there's got to be a substitution here. And it's not the denominator. We know that u equals x doesn't help. So it's got to be the numerator. Right? And the derivative of log x is 1 over x, right? So just by rearranging this, this is the natural log of x times 1 over x dx, right? So this is just the integral of u du. The natural log of 1 is 0. The natural log of, that's a 0. And the natural log of e squared is 2. So you get 1/2 u squared. And when you plug in 2, you get 4 divided by 2, which is 2. So the answer is 2. Okay. I'm out of space, so I'm going to start over. Okay, so part I, here's the integral. There's no product rule, so it's got to be a substitution, and u is probably going to be the exponent, right? So let u be negative x squared, and the derivative is negative 2x dx. We have the x, we don't have the negative 2, so just multiply and divide by negative 2. So then you just get e to the u du. Going from, well, let's see, 0 squared is 0, and then if you square the natural log of 3, you just get natural log of 3, but now it's negative natural log of 3, right? It's negative x squared. Okay, but the integral of e to the u is just e to the u. So this is just 1/2 e to the u evaluated between negative log 3 and 0. E to the 0 is 1 minus, and then 1/2 e to the negative log of 3, which is negative 3, right? Wait, no. E to the negative log 3 is e to the log of 1/3. Yeah, it's positive 1 over 3. Oops. Okay, so 1/2 minus 1 over 6. Why can't I do this? So it's 1/2 times 1 minus 1/3. So 1/2 of 2/3 is 1/3. So I think the answer is 1/3. And then part J, this will be a quick one, I think. So we're doing the definite integral from 0 to 5 of 1 plus e to the x over x plus e to the x. dx. So, yep, no quotient rule. U is the denominator because the derivative is just 1 plus e to the x. It's exactly the numerator, right? So this is going to be the integral of du over u. And what are the limits? So 1 plus e to the 0 is 2. And then this is going to be 1 plus e to the 5, whatever that is, right? So you just get natural log of absolute value of u and evaluate it between these two limits of integration. Wait, so e to the 0 is... Oh, I'm sorry. I'm plugging it into the wrong thing here. Yeah, I got the wrong limits. Hang on. If x is 0, 0 plus e to the 0 is 1, not 2. So the lower limit should be 1, not a 2 here. And then the upper limit, 5 plus e to the 5. So it's not a 1, it's a 5 plus e to the 5. Change that to a 5. Change that to a 5. And then natural log of 1 is 0. So you get the natural log of 5 plus e to the 5. And as far as I know, there's really no good way to simplify that. So that's our answer. And that completes the definite integrals in number 7. Number 8. So the tension in Newton, so it's a force, for a pendulum over half of a swing is given by this function here. So let me just copy that down. So this is just a force function. At any given time, it tells you what the force is, or what the tension is in the pendulum. And we're going from 0 to 2. So that's, again, that's half of a swing, but we want the average tension. Average tension. Right. Over that interval, right, from 0 to 2. So on the interval from 0 to 2. Right, so how do you find the average value of a function when, of course, you can't just average the two values, right? It's a whole continuum. It's a continuous function, right? Right. The graph will be some sort of a sine function. It goes back and forth. Again, we're only doing it over half of a swing, so it might go, back but not forth. So over that half swing, right, what is the average tension? I don't need that. So average value of a function, right? Average value is 1 over b minus a times the definite integral from a to b of that function. So in this case, a is 0 and b is 2. So this is just 1 over 2 times the definite integral from 0 to 2 of 8 plus 5 times the sine of pi t over 4. So we just have to evaluate that definite integral. When you integrate 8, you just get 8 times t. And when you integrate 5 times the sine of pi t over 4, well, right, there's going to be a substitution here. U is going to be pi over 4 times t. So du is pi over 4 times dt. So that means we're going to have to multiply by 4 over pi. And then the integral of sine is negative cosine, which means I'm going to have to change the plus to a minus here. Looks a little better. And now just plug in the 0 and the 2. So, oh boy, should we distribute the 1/2? So this is 4t minus 10 over pi times the cosine of pi t over 4. So when you plug in 2, you get 8 minus, So the cosine of 2 pi over 4, cosine of pi over 2 is 0, right? And then when you plug in 0, you get 0 minus pi over 10 over pi, and then cosine of 0 is 1. So I think you just get 8 plus 10 over pi. And this will be in newtons, and that should do it. Okay, number 9, not an easy one, especially if you haven't had any engineering or physics courses. It's mostly a physics problem. You have the weight on a spring, so a little picture here, you're hanging from the ceiling a spring and you attach a little weight. And if you disturb it, well, the spring is just going to bounce back and forth, right? Like this, right? Which is a sine or cosine function, right? And this is called simple harmonic motion. And you don't really have to know that here. So its position from equilibrium is given, and this is given in the problem, x of t. So x is the displacement from equilibrium. So equilibrium would be about here. That's where x is 0. So here x is positive. Here x is negative. Well, you could go the other way. So this is a times the cosine of omega t. If you want to say wt, that's okay, but this is the Greek letter omega for the angular frequency. Okay, and a is the amplitude, right? So this should look somewhat familiar, even from pre-calculus. But if not, then, don't worry about it. This is a given. This is given in the problem. And we're also given Newton's second law of motion. If you've had physics, you know very well what this is, right? And you know what it means. M is the mass. A is the acceleration, of course. In fact, I tell you that. A is acceleration, right? So from that, we want to prove Hooke's law, which is that the force is negative k times x. Right? So how are we going to do that? Right? How do we get this? Well, F is also m times a. Right? So what is m times a? The mass times the acceleration is just the mass times the second derivative of x. Right? X is the position. Right? So let's take the second derivative. Well, let's take the first derivative. Right? The first derivative is just negative a and then times omega by the chain rule, sine of omega t. And then the second derivative, let's try that again. The second derivative is just going to be negative a times omega squared, another chain rule, times cosine of omega t. Right? And if you're clever, if you put the negative omega squared in front, you notice something interesting here. This a times omega t, cosine of omega t, that's just x. Right? So it turns out, right, you just have to multiply by this negative omega squared, and so the acceleration is just negative omega squared times x. Okay. Okay. So what's mass times acceleration? Mass times acceleration, again, that's just the force. That's Newton's second law. It's negative m times omega squared times x. So what we've shown is that F is negative omega squared times x. And so now we know what this m times omega squared is. That's just k. Right? So this is, in fact, Hooke's law, which is what we wanted to show. And for part B, we know that k is just m times omega squared. Right? In part B, we want to find omega. Right? So that's just a matter of dividing by m. Right? And then taking the square root of both sides. We'll dispense with the plus or minus. We'll assume the frequency is positive. So omega is just the square root of k over m. Okay, so again, it's a good physics problem, and in fact, if you're gonna go all the way up to differential equations, this is sort of a basic problem in solving differential equations. You know, when you know the second derivative, how do you find the original function? So this is sort of a classic, basic differential equation. But again, that's all we wanted to do here in number 9. So number 10, we're assuming that f of x is defined by this definite integral from 2 to x of t cubed divided by t cubed plus 1 with respect to t. And there's 2 parts to the question. We want to find the first derivative of this function, and we want to find the second derivative of this function. Well, let's do the first derivative, right? So the first derivative is the derivative of the definite integral from 2 to x of t cubed over t cubed plus 1. Right, so there's no reason on earth we should try to evaluate this integral. This would be a hard one, but maybe a Calc 2 problem? I would, even in Calc 2, that's going to be a hard one. So yeah, the substitution I don't think is going to work very well here. Right. Instead, we're just going to use the fundamental theorem of calculus. The second fundamental theorem of calculus, right? Second fundamental theorem of calculus. Which just says that the derivative of the integral just cancels out, and you just get the original function, x cubed over x cubed plus 1. And that's it. So very easy if you know the second fundamental theorem of calculus. Very difficult if you don't, right? If you try to do this by first evaluating this integral and then taking the derivative of that, you're going to pull your hair out because it's a very hard integral to do. All right. Well, at this point here, if this is the first derivative, I think you can all take the second derivative. It's just the quotient rule. So, you know, and this is something you could have done way back in chapter 2. So, low d high minus high d low. And then the denominator squared. Oops, so that's a 3, that's a 2. So what do we get? We get 3x to the 5th plus 3x squared minus 3x to the 5th. So these cancel, and you just get 3x squared all over x cubed plus 1 quantity squared. So I think that does it. First derivative, second derivative. Again, the first derivative was, well, I'd say the hard part if you don't know the second fundamental theorem of calculus. If you do, then it's almost trivial. There's really not much to show here for the first derivative. All you have to do is state that it's by the second fundamental theorem of calculus. Okay. All right, now some derivatives. Okay, so let's just start with part A. Y is the natural log of x to the 4th minus x squared. So to take the derivative, well, this is just the chain rule, right? The derivative of log of whatever is 1 over whatever, right? X to the 4th minus 2. And then by the chain rule, you multiply by the derivative, which is 4x cubed minus 2x. And I do believe we can cancel one of the x's here, so we can take out a 2x, and that just gives you x squared minus 1 all over, take out an x, and you get x cubed minus x. So 2 times x squared minus 1 over x cubed minus x. I don't know, can we go any further? So this is x minus 1 times x plus 1. If you factor out an x in the denominator, you get x squared minus 1, which is, oh, the same thing. How about that? So in the end, this is just 2 over x. Except that can't be right. Yeah, okay, something's wrong. Oh, there's a 2 here, 2x squared minus 1, which doesn't factor. Okay, so never mind. Yeah, in the end, I think we just have to leave it. So the answer is just 4x squared minus 2 over x cubed minus x, which is, yeah, that's the answer. All right. Sorry about that. Yep, if you miss the factor of 2, you get something that's not right. So we move on to part B, x e to the x minus x. Again, we want the derivative, right, not the integral. So, well, we know the derivative of e to the x is just e to the x, but this is a product, right? So we apply the product rule. First times the derivative of the second, plus second times the derivative of the first. The derivative of x is 1, and then minus the derivative of e to the x is e to the x. So we just get x e to the x plus e to the x minus e to the x, and that, of course, is just 0. So you're still left with x e to the x, and that's it. This is one you might want to remember, because notice what happens if you want to take an antiderivative, if you want to integrate x e to the x. Well, you just get the original function. You get x e to the x minus e to the x, right, plus c. Again, there's no product rule, so how you get this is by parts. So that's a Calc 2 problem. On the other hand, I just figured this out by working backwards. If you know the derivative, then you take the integral of the derivative and you get the original function. No matter, that's right, that's for another problem. And then part C is log x over x squared. Again, find the derivative, g prime of x. So it's quotient, so maybe the quotient rule. On the other hand, this I think might be better for a product rule if it's x to the negative 2 times log x. I think I prefer that in this case. So first times the derivative of the second, the derivative of log x is 1 over x, plus second times the derivative of the first, so that's negative 2x to the negative 3. So what do we get? We get 1 over x cubed minus 2 log x, also over x cubed, so we already have a common denominator, 1 minus 2 log x, all over x cubed. Okay. Part D, e to the t over log t. So the derivative of y with respect to t, I think here quotient rule makes sense. So denominator squared, so low d high minus high. The derivative of log is 1 over t. So we can factor out an e to the t here, and we just get log of t minus 1 over t, all over the natural log of t squared. You know, just get rid of the denominator here, so multiply by t over t, you get t, e to the t, yeah, t e to the t log t, and then minus e to the t, all over t log of t squared. And I think you can factor out an e to the t in the numerator, but, you know, good enough. And then part E, so z is the natural log of 1 plus e to the x over 1 minus e to the x. So this looks like this would involve, first of all, the derivative of log, right? So that's going to be a chain rule. And then the derivative of what's in the parentheses is a quotient rule. If you want to do it that way, go right ahead. Before taking the derivative, however, this is the log of a quotient. It's just the difference in the logarithms. So we turned a quotient rule into a sum rule, or in this case, difference rule. So the derivative is just 1 over e to the x, and then by the chain rule, the derivative of 1 plus e to the x is e to the x, right? Minus, and then 1 over 1 minus e to the x, and then the derivative of 1 minus e to the x is negative e to the x. So this, we're going to end up adding these. Plus e to the x over 1 minus e to the x. And that's good enough. Or you can get a common denominator, which is just going to be, let's see. You can factor out the e to the x. So 1 minus e to the x plus 1 plus e to the x all over 1 minus e to the 2x. So this adds up to 0. So I think we just get 2 e to the x over 1 minus e to the 2x. And yep, so this is how I wrote, this is how it's in the answer key. I would be okay with this up here. You know, you should get a common denominator, but either way is fine, I think. And then part F. So h of x is x to the power cosine x. Okay, so we can't use the power rule because this is not a constant, right? It's not x to the 2 or x to the 3. Cosine of x depends on x, right? And we cannot use this rule either because now a is, right, the base is not a constant either. So both the base and the exponent are functions of x, right? This, by the way, is just, a to the x times log a. But we can't use that either here, right? So, yep, our only option is to first take the log of both sides. Logarithmic differentiation. That's the trick here, right? So before we take the derivative, let's bring the exponent in front. So this is cosine of x times log of x. Now we can take the derivative, right, of both sides. So on the left side, the log of h of x, the derivative of that is just 1 over h of x times the derivative of h. So h prime over h. And on the right, well, this is going to be a product rule. So first times the derivative of the second plus second times the derivative of the first. So the derivative is minus sign times log x. So now just multiply both sides by h of x, right, and on the left they cancel, so you get the derivative of h when all is said and done. And can I move this in front? I think that's how it looks in the answer key. X to the power cosine of x times cosine of x over x minus sine x times log x. And that's good enough. Yeah, don't try to simplify that. It's not worth it. All right, so I guess I'll do I'll do the rest. Okay, so yeah, this is kind of a tricky one. So I guess it's a good thing we're going to do it here. In particular, we're taking the derivative, right, of a definite integral. And this is one we've done not that long ago in this video by using the second fundamental theorem of calculus. This is a 5, by the way, right? On the other hand, the problem is that this is not a number. It depends on x. So what we're going to have to do is pick a number between 2x and x squared. Obviously, it depends on what x is, but let's just say it's 0. it really doesn't matter what that number is, right? So if we split this up, this is going to be 0 to x squared, right, plus the integral from 2x to 0 of the same thing. Oh, I forgot my dt here, right? dt. And we're taking the derivative of the sum, so that'll be the sum of the derivatives, right? On the other hand, this is in the wrong order, right? So if we have to invert the limits, I'm getting tired of writing all this, we just subtract, right? We take the opposite. Okay, now I think we can finally use the fundamental theorem of calculus, or the second fundamental theorem of calculus. You're just going to get the square root of 1 plus x squared to the 5th times the derivative of x squared is 2x, right? So that's chain rule, right? Minus square root of 1 plus, let's see, 2x to the 5th. And then the derivative of 2x is 2. That's also by the chain rule. So in the end, we're just going to get 2x square root of 1 plus x to the 10th minus 2 times the square root of 1 plus 32x to the 5th. Okay. So yeah, tricky one if you don't know how to split it up into the two parts here. Oh, yeah, I mean, the property, I think this comes from section, I want to say 4.4, either 4.3 or 4.4. Right? We go from A to C plus from C to B. Right? So my A here was 2x, my B was x squared, and I picked C to be 0, although it could be, doesn't matter what it is. It's just some constant. I probably should have just left it as C here instead of putting 0 there, but it doesn't matter. You get the same thing regardless. All right, and then finally, log of x cubed times tangent squared. So log of x cubed times tangent squared. And what is this? Y. So to take the derivative, actually you could do this two ways. If you don't want to do the product rule, you can just do the sum rule. And even then you can bring the power in front. Right. So now taking the derivative is pretty routine. You're just going to get 3 over x plus 2 times, okay, 1 over tangent, and then the derivative of tangent is secant squared. But I think we can leave it at that, right? So in the answer key it says 3 over x plus 2 secant x times cosecant x. I'm wondering if I missed something here. So secant is 1 over cosine squared, and tangent is sine over cosine. Yep, so you cancel, oh. Okay, derivative of tangent, derivative of log of tangent is 1 over tangent, and then by the chain rule, the derivative of tangent is secant squared. So secant squared is 1 over cosine squared. And then you just cancel one of the cosines. Yeah, that's right. Cosine times sine, right? Which is secant times cosecant. Okay, it works. And then just multiply by 2. Okay, so either way, I don't know, I would have left it this way, but this way is a little bit simpler. All right, so those are the derivatives. And now we get to the inverse function. So we're going to need, probably for this and other problems, we're going to need the following property, that if you want to find the derivative of the inverse of a function at a specific number, I'll call it c, you can also take the reciprocal of the derivative of f of the original function, right, not the inverse, but then you have to evaluate that at the inverse of f at c. It's a very important rule here that I think we're going to need to do that here. Okay, so what do we know? We know that f of x is defined as this definite integral from 2 to x of dt over the square root of 1 plus t cubed. Don't even try to evaluate that. I wouldn't even know how to do that, right? So this is a big question mark. What is this function? Explicitly, we don't know. We only know it as an integral, as a definite integral. And the question is to find the derivative of the inverse at 0. Okay, question. So what is that value there? Okay. So yeah, unfortunately, I don't think we're going to be able to do this directly. After all, how do you even find the inverse of the function if you don't even know what the function is? Let alone then take the derivative of that. So yeah, that's not going to work here. It's not going to happen. Right? On the other hand, we know how to take the derivative of this. We did it a couple times already, right? Second fundamental theorem of calculus. Right, and so that's what we're going to need here. We're going to need the derivative of the function, but it's the derivative of an integral, 1 over the square root of 1 plus t cubed, right, dt. So that's just 1 over the square root of 1 plus x cubed. Okay, so that's the derivative. Now, what do we have to do? Well, now we have to plug in, so we have the derivative, but now we have to plug in f inverse of 0, right? Because that's my c here, right? Here c is 0. Okay, so that's another problem here. What is f inverse of 0? Well, we never found the inverse, right? In fact, we still don't know what f is. How are we supposed to find the inverse? So just think about what the inverse at 0 is. It's going to be a value of x, right, such that if I plug in x into the function, I get 0. Right? So in other words, we just have to solve this equation. So we have to solve f of x. Remember, f of x is this definite integral. So where's this definite integral equal to 0? For what value of x? Yeah, don't think too hard here, right? The definite integral of any function from a to a is 0. So if the lower limit is 2, well, that has to be the upper limit, right? So x has to be 2. See how easy that was? Again, you have to know this property here, but, you know, that's back in chapter 4, right? 4.2, 4.3, I think. 4.3. So, yep, look that up in section 4.3. So, x is 2, right? Which means f of 2 is equal to 0, or f inverse of 0 is just the number 2. So that's what we're going to plug in to the derivative. We're going to plug in 2 here. In fact, let's make that explicit. This is 1 over the derivative of f at 2. So here's the derivative of f. Sorry, I'm running all over the place here. Okay, so let's copy it down here. The derivative of f is just 1 over the square root of 1 plus x cubed. Now plug in 2, right? So be careful. You can't plug in 0. You're plugging in f inverse of 0, which is 2, right? So 1 over the square root of 1 plus 2 cubed. Well, 2 cubed is 8, 1 plus 8 is 9, and the square root of 9 is 3. So this is 1/3. Okay, so we're almost done, right? That's f prime of 2, but be careful, that's the reciprocal of that, right? So it's 1 over 1/3, which is 3. And that's the answer, right? So the derivative of f inverse at 0 is just the number 3. Okay. All right. All right. I guess we'll do one more. Number 13. So find the derivative of f at 2 if f of x is equal to e to the g of x, where g of x is this integral, right? So yeah, here we have to be careful because f of x is e to the integral of 2, the integral from 2 to x of t over 1 plus t to the 4th dt. So this might seem a little unusual to have an integral as the exponent, but if you're going on to, higher calculus, calculus 2, and certainly in differential equations, I would say get used to it because this is not an uncommon thing to do. So if this is the function, how do we take the derivative, right? So let's just write it as e to the g of x first, right? We know what g of x is. It's the integral. So how do I find the derivative of that? Well, it's the derivative of e to any power. It's just e to that power, right? Don't forget the chain rule, though. Then you have to take the derivative of the exponent, the derivative of g, right? And so what's the derivative of g? The derivative of g is once again by the second fundamental theorem of calculus. You see a pattern here, right? We've had to use that quite a lot here. This is just going to be x over 1 plus x to the 4th. Okay. So in the end, we just get e to the g of x times x over 1 plus x to the 4th. And I guess now we can plug in 2, right? What's f of 2? Oh, I'm sorry, that's f prime of 2, right? It's going to be e to the g of 2 times 2 times 1 over, or rather, over 1 plus 2 to the 4th. Okay, and what's g of 2? G of 2 is the, well, again, I'm running out of places here, but g of, okay, so g of 2 is the definite integral from 2 to 2, and you know what that is, right? That's just 0. Sorry, it's 0, right? Okay, so e to the 0 times 2 over 1 plus 16. E to the 0 is 1, so 2 over 17. Okay. All right, one more. I know I'm getting tired, and it's been a long video, so all right, last one then. Okay, so we're given a function. Let me just copy it down so we can all see it here. It's the log of the cosine of x. And again, don't worry about the domain of this kind of a weird function here. We should be taking the absolute value of cosine, and that way it's defined for all x. But here it's only defined, I believe it's between, minus pi over 2 to pi over 2, and then just add multiples of 2 pi to that. But it doesn't matter. I think it all works out here. So we want to find the derivative of the inverse function at x equals negative log 2. Right, so in other words, we want to find the derivative of the inverse plugging in negative log 2. Okay, so, well, we can certainly find the inverse. I think that's not too hard. But then can we take the derivative? good luck with that. So I think we're going to do this the indirect way again. All right, if we want the derivative of the inverse at a specific number, we're just going to take the reciprocal of the derivative of f and then plug in f inverse of c. In this case, this is going to be c is negative log 2. So maybe let's do that first, right? What's the inverse at negative log 2? Well, it's just some number x such that f of x is equal to negative log 2, and f of x is log of cosine of x. So let's just solve this equation. Where's this negative log 2? So that minus sign is kind of irritating because otherwise they'd both be natural logs, right? Well, you know the trick, right? This is going to be negative 1. We can take that into the exponent. So this is the natural log of 2 to the negative 1. But 2 to the negative 1 is just 1/2. So where is cosine of x equal to 1/2? Oh, by the way, log is a one-to-one function, so you're allowed to cancel the logs, right? So yeah, why can I cancel the logs? Because it's 1-to-1. All right, so where's cosine 1/2? Well, there's a lot of solutions to that, but I think the main one is going to be pi over 3. You could do negative pi over 3, but pi over 3 works, right? Yeah, so that's the inverse, right? Pi over 3 then. So in other words, we're going to take the reciprocal of the derivative of f at pi over 3. So what's the derivative? Well, we didn't do that yet. So f prime of x, log of cosine of x. So the derivative of log of cosine x is 1 over cosine of x times the derivative of cosine, which is negative sine. So that looks like, oops, not cotangent, negative tangent. So now we just plug in pi over 3. So negative tangent to pi over 3 is negative square root of 3. And then when you take the reciprocal of that, you get negative 1 over the square root of 3. Or if you rationalize the denominator, it's negative square root of 3 over 3. And a quick check with the answer key, because I'm hoping that's correct. Yep. So either way, again, you don't have to rationalize the denominator anymore. Oops, sorry. So I would accept either. But again, the second one's in the answer key. So if you get the first answer and think you're wrong, it's because you don't know how to rationalize the denominator. So I hope you know how to do that. Anyways, so that's the entire practice test. Wow, I'm pretty sure I covered just about everything. I don't remember skipping anything. If I did, then it was hopefully an easy one. All right, well, good luck. Good luck on test 4.